Okay, so let's get started. So this is MSE 498. So we have 27 folks enrolled. So we do have a couple spare machines. So if you're not in the class, that's okay. Thanks, as long as there's spare machines. So if you just pass around the sign-up sheets, that'd be great. Okay, so last time we started working with MATLAB, and so the idea was we're trying to introduce you to the vocabulary of MATLAB so that you were able to start doing some elementary things. The most basic of which, and perhaps one of the most important of which, is starting to make some plots. And so we ran through some plotting stuff last time. How do you make a histogram? How do you make a three-dimensional histogram? How do you make a scatter plot with a heat map attached to it? All those sorts of things. And so I gave you the code for that. And so, like the bash lectures, this is meant to serve as a library to you. So I'm trying to illustrate these things to you. And when you want to use them, you can come and look at the code in those slides and actually make the plots yourself. And so I was encouraging you also to start playing around with it, start, executing MATLAB codes, making mistakes, looking at the help, all that sort of stuff. And so obviously I'm available to talk to you about any problems that you might have with that, but you're going to get some practice during the project that we do to kind of put this into practice. Okay, so are there any questions last time about any of the plotting stuff anybody was worried about or having difficulty with? Okay, so today I thought we'd start to do two things. I'm going to introduce you to some data analysis, and so running some pretty powerful, actually, MATLAB data analysis techniques based on some sort of reasonably advanced statistics. And so some of these statistics you may not have actually seen before, and so I'm going to introduce you to the statistical theory in sort of one slide, and then the MATLAB code that actually executes the theory in the next slide. And so if you've not seen this statistics before in any of the classes you've taken, don't worry about it. I'll give you what you need to know. But it's really a very powerful way of analyzing data, using basically like 1 or 2 lines of MATLAB code. So that'll take probably 45 minutes or an hour. If you want to follow along and type in the commands, everything's going to be based on that water_models.csv file. So you can load that into your workspace and start making these analyses yourself. Or you can just watch the lecture and just understand the code that I write up on the board and then actually put it into practice yourself when you do the project. So it's up to you. I'll try and go reasonably slowly so that you have time to sort of type the commands if that's what you want to do. So I'll take like 45 minutes or an hour, and then I thought we could spend the balance of class actually working on the project together. And so I'll hang around until the end of class, and if you want to work on your bash or your MATLAB project, I can answer any questions you might have. Sound good? Okay, so let's get going. So data analysis using MATLAB. Okay, so we made things like plots like this before, and so you can make the scatter plot with the blue dots here using some of the code that I showed you last time. But what if you want to do something more advanced? What if you actually want to fit a line to it, fit a polynomial curve, or compute a correlation coefficient, or do some other statistical analyses? So these are all nicely built into MATLAB. And so I'm going to run through some of the most important ones. Of course, there are many, many others, and some of these you're going to use in your homework. Okay, so who's familiar with Pearson's correlation coefficient? Anyone heard of this before? Okay, so Pearson's correlation coefficient basically is a measure of the linear correlation between two variables, and it's bounded by -1 and 1. So if two variables, x and y, are perfectly linearly correlated, meaning they lie on basically a straight line, regardless of the gradient of that line, they will have a correlation coefficient, a Pearson's correlation coefficient of 1. If they lie on a negative line, they will have a Pearson's correlation coefficient of -1. So it tells you how linearly correlated two variables are. This is a very nice thing that we want to do all the time when we're doing mathematical analyses. So just showing you some examples here. These points are all lying on a line pointing upwards. This is a Pearson of 1. These are all lying on a line pointing downwards. This is the x-coordinate. This is the y-coordinate. So it's fundamentally a 2-coordinate measure. This is -1. And then you can interpolate between them. And so maybe you have a bunch of scatter, but it's still pretty linear, so maybe -8 comes out as your correlation analysis. If you're completely uncorrelated, so basically just a messy 2-dimensional Gaussian lying in the plane, you're going to get a Pearson of 0. And so that tells you they're linearly uncorrelated. Okay, so much for the top line. The second line, I'm trying to show you the gradient doesn't really matter. So it doesn't matter whether you lie on a steep line pointing up or a shallow line pointing up, you're still going to get a Pearson of 1. However, once you pass through the horizontal and start pointing down, you're going to get a Pearson of -1. And the special case where they lie perfectly horizontal is sort of undefined. So that's where Pearson sort of breaks down a little bit. This is great because maybe we want to measure two things about a system. Maybe we want to measure its Young's modulus and its cohesive energy of a metal, perhaps. And maybe those things are very linearly correlated. So maybe if you know the cohesive energy, you have a good measure of the Young's modulus. Or maybe they're completely uncorrelated, and knowing one doesn't provide you any information about the other. And so Pearson provides you a way to sort of assess that in a very quantitative way. Okay, so then just one word about this before we get into sort of the math part of it, is it does not measure nonlinear correlation. So it only measures linear correlation. So you can make nice nonlinear pictures, so things could lie on a circle, or on this sort of smiley face, or on this weird sort of scattered sine curve, and Pearson's probably not going to give a good representation of whether those are correlated or not, because the correlation is nonlinear. So that's where Pearson fails, and you have to do something more sophisticated. But as sort of a first analysis of correlation, Pearson is absolutely the right thing to do. Just be a little careful when you apply it. Always visualize things to check that, you do a sanity check that it's sort of making sense. And so visualizing the points is also very useful. Okay, so that's what Pearson's is, sort of in words. What is it in math? It's very simple. So this is the Pearson correlation coefficient. Rho it typically goes by, or maybe a little r between x and y. And so it's a quotient. The top line is the covariance between x and y, and then we normalize it by the standard deviation of x and the standard deviation of y. So it's basically like a normalized covariance, might be the right way to think about it. And so this is the sort of expansion of the covariance on the top there. Okay, so a covariance, but we're normalizing with respect to the standard deviation of each variable individually, because we don't want to worry about whether things are very widely spaced in x and very narrowly spaced in y. So it's just a normalization. Yeah, Sam.
So on the bottom row, the second grade from the left, those would still be zero, even though it's sort of slanted upwards?
So these guys here?
Yeah, the two squares.
Yeah, so it turns out that, these are cooked up examples, and so it turns out they're cooked up in such a way that the stuff that points up precisely cancels the stuff that points down. If you had something that wasn't such a synthetic example, maybe it was slightly skewed towards the north, you would get maybe a positive Pearson. Okay, yes, these are super synthetic. Yeah, good question. Okay, so people have a sort of a handle on what Pearson does, measures linear correlation. If that's all you remember, that's great. Then you can come and look at the slide for more information. That's absolutely fine. So how do we implement this in MATLAB? So if you have imported your data, like we showed last time, you will have two vectors, one of sigmas, one of epsilons, that we pulled in from that water_models.csv file. So you can type this code in if you want to follow along. So the call to MATLAB is corcoef, C-O-R-R-C-O-E-F. I seem to have some mental block when I always miss the second R, and MATLAB complains. But you can always look up the help. And then you just provide the x and the y. So those are the arguments to this function. And then this is the output to this function. And so it outputs stuff into these little variables you write here, R, P, R underscore lower, R underscore upper. So the function makes the call on our data, and then it outputs stuff to here. And so that's the interesting stuff we're going to look at. Left. And so this little variable R is a 2x2 matrix, which holds the Pearson correlation coefficient for XX, XY, YX, and YY. And so the XX and the YY, the diagonal terms, better be 1, because you're looking at the correlation of yourself with yourself. And so the interesting thing actually happens on the off diagonals. And so it's a symmetric measure. It doesn't matter whether you do XY or YX, so that's why these guys are exactly the same. And so it turns out our Pearson correlation coefficient for our data is 0.24, which is actually pretty weak. And so a strong Pearson is like greater than 0.8. A weak Pearson is like less than 0.2, just as a general rule of thumb. And so these things are pretty weakly correlated. And so that's a finding that we've already developed from our data. Okay, and so then we're going to delve into a little bit more statistics. And so are people familiar with p-values? Have people heard of this, a p-value? Okay, so we're going to use this a little bit in this course. And so the idea is that perhaps you can develop some sort of null model for your data. A null model meaning like a baseline assumption about your data. And you can see whether or not the data conform to that baseline assumption using some statistical tests. Okay, and so the classic null model is things like it's boring. And so the null model we adopt in this case is that they're uncorrelated. So the null model we're going in with is that x and y are uncorrelated. So it turns out if we assume that, and we assume a couple of other things about our data, that there are uncorrelated Gaussian distributions, which may or may not be true, but usually it's a reasonable assumption to make. At least for a first cut analysis. It turns out that our null model conforms to a particular distribution known as student T distribution, and we can see how far our data actually deviate from this theoretical null model. So without getting into too much of the details, we're adopting some theoretical null model and seeing whether or not our data conform to that. So if our data do conform to that, they are uncorrelated, and we can say that with some statistical precision, which I'll show you in a second. If they do not conform to that, we can say they are correlated. They do not obey the null hypothesis, and we can assign a statistical precision to that also. It's a little bit subtle, but does that sort of make sense to folks? So we go in with some null hypothesis, and we see whether or not that is satisfied by our data. And so that's what's happening right here. We're basically going in with the null hypothesis and saying, what is the probability that the observed Pearson's R value, so this value of 0.2441 that we saw, occurs by chance, given that the null hypothesis is true, given that the data is actually uncorrelated? So the subtle question we're asking, we're saying, okay, imagine the data is uncorrelated. Okay, that's our assumption. But then we have finite data, so it's going to have noise in it, there's going to be mess in it, it's not going to be a perfect measure. So we compute our Pearson. We get 0.2441. What is the probability that value arose just by chance, just by perhaps because we didn't have enough data, or just because we took a particular sampling of data from our distribution? So if we can say what is the probability that arose by chance, we can then assign some confidence to the Pearson value that we calculated. If it's a very low probability this arose by chance, we can have great faith in this value. If there's a very high probability this arose by chance, maybe we say we don't have much faith in this value. So it's like some meta-knowledge about the data. So it's like somebody tells you a fact, and whether or not you believe the fact is how trustworthy you believe that person is. So if they're a trustworthy person, maybe you assign a high sort of quality to that fact. If they're a liar, you want to assign a low quality to that fact. And so that's what that p-value gives you. So it's sort of a meta-analysis. Okay, and so that's what's happening here. So we compute this p-value. The probability that this value of the Pearson's correlation coefficient arose by chance, given our null hypothesis that the data is uncorrelated, is 28.6%. And that's actually pretty high. Usually we like to see things lower than 5%. And so if this is lower than 5%, typically we have good confidence in this. If this is higher than 5%, we say, well, actually this could have arisen by chance, so we don't actually have much faith in this value. So does that make sense? I know it's subtle if you've never seen this before. You'll get some practice in your homework. If this still is just sort of sailing right over your head, come talk to me and we'll figure it out. So we're going to see a couple other examples of this very shortly, and so you'll have another chance to take a look at this. Okay, and then there are 95% confidence intervals. And so people heard of confidence intervals? So it's sort of the limits on the confidence of your value. So that's another way of assessing how confident you are in this particular value. So we can appeal to the null hypothesis distribution, and we can say, well, okay, this is the value we actually got, but can we put some error bars on this value? And MATLAB does that automatically for you. And it says the lower error bar at a 95% confidence is going to be -0.2, and the upper error bar is going to be 0.61. So there's actually a really wide range in this value of 0.24. And so you can see just by doing this analysis, we only get a small amount of knowledge. We get a single scalar value. But by supplementing it with this p-test, the p-value, and the confidence intervals, we have a much better handle on how certain we should be of this particular value. Okay, so any questions about that so far? Okay, so you can all now run a Pearson's correlation analysis. And so you can all run this very simply, and now you have some ability to interpret the results that MATLAB will give you. Okay, so you should stick your hand up at any time if you're feeling uncertain. Okay, so we're going to move on to the next test. And so this is a permutation test. And so one of the deficiencies of Pearson's sort of p-value analysis is that you have to assume some null hypothesis. And so it turns out the null hypothesis that's appropriate there is that the data conforms to the student p distribution. So don't worry about what that is, but it's some mathematical distribution that we're going to use in order to give us a p-value. So what if we don't know what distribution to use? Can we sort of do a similar analysis empirically? And so that can happen. Perhaps we have data that we don't really believe conforms to a particular distribution. In particular, let me go back one slide. If we know for a fact that our data do not look like Gaussian distributions, maybe this is going to be a terrible thing to do. And so maybe we can do something empirically where we don't have to appeal to some underlying mathematical theory, and we can actually just run our data and test it sort of self-consistently and see how good of a prediction we can make. So that's what we're going to do with a permutation test. It's known as a non-parametric hypothesis test because we don't have to assume a distribution. And the question we're asking basically is the same as for Pearson. What is the probability the observed result occurred by chance? So maybe you just don't have very much data. And so there's going to be a bunch of noise in it. And so there's a high probability the result you get is just random. It's just happened by chance. So how are we going to do this? So empirically, we're going to do something very simple. We're going to randomly shuffle the data and recompute the test statistic. And so what we have in our particular example is a column of epsilon values and a column of sigma values, and they occur as pairs. And so for every particular water model, we have a value of epsilon and a value of sigma. And so what we were doing with the Pearson test was testing how correlated those things are. So what we're doing with the permutation test is that we say we're going to go in and artificially break the correlations by scrambling these. So we're going to scramble the elements of these vectors. So we're going to randomly pair epsilons with sigmas and screw up our data set. And then we're going to recompute our test statistic, our Pearson correlation coefficient. And so what we should see is that if the data really are correlated, when we scramble it, the Pearson correlation coefficient should crater. It should go down to 0. And if we compare that to what we get when we do the Pearson correlation of the unscrambled data, there should be a very big difference. Whereas, on the other hand, if the data are intrinsically uncorrelated, scrambling it should not have very much effect on the Pearson correlation coefficient. Does that make sense? So we're sort of artificially going in and breaking all the correlations and saying, what does that do to our Pearson correlation coefficient? Does it have a big impact or a small impact? And so in this case, the way we're going to compute the p-value is not by asking MATLAB to do some crazy stuff we don't really understand under the hood. We're actually just going to compute it in this very simple-minded way by the proportion of shuffled test statistics that are greater than the observed value. What does that mean? We take an observed value. We get 0.2441. We do a bunch of scrambles. Some of the scrambles yield values of the Pearson correlation coefficient that are less than 0.2441. Some of them yield values that are greater than 0.2441. And so if we compute the proportion that are greater than 0.2441, that gives us some handle on how probable this value of 0.2441 could have happened by chance. So it's an empirical measure of, you just scramble your data, how probable is it you get a value of 0.2441 or higher? And that tells you how probable that will happen by chance. Does that make sense? Okay, so let's see that in practice. So how do we do this? So we need a few more lines of MATLAB code because we're not running this just using a built-in MATLAB function. We're actually doing some stuff manually. And so how does this actually work? Okay, and so what we're going to do is we're going to call car coef between sigma and epsilon. R underscore obs is going to be our 2x2 matrix. And so in this case, we're not worrying about all the ancillary stuff. We don't want MATLAB to bother calculating the p-value or the confidence intervals. And so that's why there's only one variable on this side of the call. There's only one output variable. Again, if you go to the help for car coef, you can see how many variables you can put on the left-hand side, how many MATLAB's expecting, whether you have 1, 2, 3, 4, and what those variables actually correspond to. So in this case, we're making a sort of lighter call when we just want the first one. Okay, and so then we said we're interested in the off-diagonal elements. So element 1, 2, you could have also picked 2, 1. And we saw from before that was 0.2441. So this is all repeat so far. So this is the Pearson correlation coefficient for our data, 0.2441. Now let's do the permutation test. This is a little more involved. First of all, we compute how many elements in our vectors that we have. So n is just the length of the sigma vector, or equivalent to the length of the epsilon vector. And we say we want to produce 1,000 different tests. Okay, so we're going to do 1,000 empirical permutation tests. We're then going to pre-allocate an array to hold the values of all those tests. So our R underscore array starts life as an array of zeros with 1,000 elements. So it's a 1,000 by 1 column vector. So in MATLAB, it's always good practice to pre-assign containers. So pre-assign your vector, pre-assign your matrix. It just makes things happen faster and it has better memory management. Okay, so we're going to dump into this vector the value of the test, the Pearson correlation coefficient under 1,000 independent scrambles. So that's what's going to be held in there. So let's actually do the scrambles. So we have a nice for loop. So just as we saw in Bash, the syntax is a little bit different in MATLAB. So for I equals 1 colon n tests, so for 1,000 different tests, we're going to scramble the data. And so IDX is a random permutation of n numbers. And so n is the number of data points that we have. If that was 36, basically randperm just scrambles the integers 1 to 36. So it might go 2, 10, 26, 28, 4, 5. It's just a scrambling of those numbers, which is completely independent each time you call it. Then we're going to compute the correlation coefficient between the sigma vector, which is unscrambled, and the epsilon vector, which is scrambled according to this IDX. So let me explain that. So the call to rand perm is going to give you a vector that looks something like this. So imagine n is equal to 5. Rand perm is going to make this vector look like 5, 4, 1, 3, 2, or something like this. So it's a random scrambling of the integers 1 through 5. When you then access the epsilon array with IDX, it's going to permute the elements of this array according to this ordering. So the first element of this object is going to be the 5th element of the epsilon array. The second element of this object is going to be the 4th element of the epsilon array. So it's just doing this scrambling in a very sort of concise way. Yeah, question? Just pick some big number. So it has to be greater than sort of 100 maybe to be statistically meaningful. This is actually going to be a very quick test, so we could do 1,000. Actually, in these machines, you could probably do 10,000. So that's sort of the simple answer. The real answer is it needs to be big enough that your results are not sensitive to that value. So your number of tests needs to be big enough that if you, say, double the number of tests, you don't get a different answer. So yeah, good question. Yeah.
Will this often return a similar value to the value from the test?
Sometimes and sometimes not. If the conditions of the Pearson test, the data are Gaussian distributed, is a good assumption, then you would expect them to sort of line up pretty well. If you violate some of the assumptions that underlie the Pearson test, then they can differ by quite a lot. Yeah, so if you have time, it's always good to do both, and then you have 2 independent estimates. Okay, and so we do the scrambled epsilon. We could have equivalently scrambled sigma, it doesn't matter, or you could scramble both, but that's redundant, so we just scramble one. And then you recompute Pearson. And so we have Pearson stored in R, we pick out the off-diagonal element, and we store it in our array that we pre-assigned there. So is everybody okay down to here? Even if you're not sort of familiar with the syntax, you sort of understand what it's doing, and at least you could type the syntax in and you could reasonably expect what would happen. Okay. And so then we have to actually do what we stated we were going to do, which was say, under all these scrambles, what is the probability that I observe a Pearson correlation coefficient greater than 0.2441? So when I artificially break the correlations, what's the probability I get this value or higher? And so that's exactly what we're doing here. And so what we're doing is sum of the absolute values of the R array, so we're not worrying whether it's plus or minus. We can talk about that later, but really we're just looking for a strong correlation. It doesn't matter whether it's strong positive or strong negative. You could think about worrying about the sign, in which case your call here would be slightly different. And we're saying, so how many of the values of this array are greater than 0.2441? And then we're just dividing by the number of elements in the array to get a fraction. And so it turns out the fraction is 26.3%. And so again, that's actually quite big. And so the probability from this empirical estimate, we would get this value for Pearson or higher is like 26%. And so we would say we don't actually have much faith in this value because there's a high probability it would arise by chance. And so the right way of saying this is that's right. And so then you have to define some cutoff and you say, I'm willing to have faith in this value at a confidence level of X%. And so typically that's 5% or 1%. And when this value is less than 5% or less than 1%, then you accept this as being a good estimate. And so that X value is up to you to choose. As I said, it's usually 5% or 1%. Okay, so that's a permutation test. So any questions about that? People feel like speed's okay, we're not going too fast, we're not sort of blowing through this too quickly. So I know a lot of folks haven't taken these sort of stats things, which is why I'm introducing them. But at the end of the day, if you can type this into MATLAB, you're going to be fine. Okay. The Bootstrap. So has anyone heard of the Bootstrap or the jackknife? Okay, so this is another really cool technique. So we saw the p-value, the Pearson correlation coefficient from MATLAB can give you p-values and confidence intervals. And we said if we think the data violates those assumptions, maybe we can empirically compute the p-value using the permutation test. Is there a way to empirically compute the confidence interval? Yes, you can use the Bootstrap. So again, this is a non-parametric, meaning empirical, so we don't make any assumptions about the data, estimate of a test statistic confidence interval. So without assuming a distribution, so the student T distribution that we had to assume in the first slide, we're answering the question, given our finite sample, what range of test statistics might we have seen? And so the fundamental idea is that we have a limited amount of data that was sampled from perhaps a bigger population. So imagine we were interested in the average height of a student at the University of Illinois. So one thing we could immediately do is that we could measure the height of everybody in this room, take the mean, and we could say maybe that's a good representation for the average height of a student at Illinois. Of course, we haven't measured the entire population, and so it's just an estimate. So perhaps it turns out that particularly tall people really like to take computational materials science and engineering classes, and so our estimate is skewed up. So how would we know that that estimate was skewed up? Or how would we know how good a job we're doing where all we have is the heights of the people in this room? We don't have the heights of the entire population. Can we make some sort of on-the-fly estimate for how good a value that is? So that's exactly what the Bootstrap is doing. It's saying, what range of values of our test statistic, in this case the height, might we have seen if we'd taken a different sample of people, if we'd measured the heights of people in MSE 201 or CS 101? Imagine we'd taken those heights. Would we have got a very different result, or would our result be very similar? So that's the question. Okay, and so that's what we said right here. And so different samples of n data points will give different results, clearly. So the Bootstrap simulates different samples by resampling with replacement. And so we don't have all the heights of all people in the entire university. All we have are the heights of the people in this room. And so maybe we can resample our data with replacement. And so maybe there's the height of student A, which is sort of 1.2 meters, say, student B, 1.1, student C, 1.2, student D, 0.9, student E, 0.8. So imagine these were the heights. So I'm European, so we're measuring things in meters of these students in the room. And so we could compute some mean according to that. So that's a very easy thing to do. Now the Bootstrap comes along and says, well, imagine you didn't have these 5 measurements. Imagine you had 5 different measurements. So how can we possibly get 5 different measurements when these are the only 5 measurements we have? It seems impossible. But it turns out, and the mathematical theory for this is very robust, that what you can do is resample with replacement. So imagine I resample with replacement. And so what does that mean? I throw a random number between 1 and 5, and I pick out the corresponding value. So perhaps my random number is 3, and so I get C 1.2. I throw a new random number between 1 and 5, maybe I get 1, and so I pick out A, which is also 1.2. I throw a new random number, maybe I get 3 once again, and so then I resample C. Imagine I get 1 once again, I resample 1. Then I get 5, and so I resample E. So I have 5 new measurements that have been resampled from this data set, but with replacement. And so every time I pull one, I put it back in the pool, so I can resample it again. And so perhaps, and it turns out the math tells you that this is true, this is a good sort of, well, it's really the best thing that we can do to make a sort of guess of what 5 measurements we might have seen if we'd sampled a different part of the population. That sort of makes sense. It's a little weird because typically you sample things more than once, but it's sort of the best we can do with finite data. And so n equals 5 here, n equals 5 here. The original data set, they're all independent measurements, but in the resampled data set, you can have some duplicates and have some that are never sampled at all. So that's resampling with replacement. So pretty simple operation. Okay, so how do we put this into practice? Okay, so here's the MATLAB code. We compute n, which is the length of our sigma vector. We do 1,000 tests. We could do a different number of tests. We assign the value true to this replacement flag, which we're going to use in 1 second. So there's nothing fancy going on here. This is just a variable called replacement, and it happens to have the value true. So that's fine. And then we pre-allocate our R array, which is going to be 1,000 by 1 vector, which is going to hold our results. Okay, so that's setting up the problem. Let's do the resampling with replacement. So we're going to do for I equals 1 to 1,000. These are the indexes of the things we're going to resample. And so we have 1, 2, 3, 4, 5. We want to generate some vector that looks like maybe 3, 1, 3, 1, 5. And so that would pull out precisely these values from this array. Of course, we want this to be random, so we're pulling out different ones every time. So there's a very clean one-liner way to do this in MATLAB. We call rand sample. We're sampling from n values. So we're sampling from a possibility of 5 values. We want to pull out 5 values. These CUDA imprints will be different. And we want to do it with replacement equals true. So you could just write true here if you preferred. And so that's going to do exactly this procedure. So then we go in and we compute the correlation coefficient between sigma with these indexes, so the random resampling, and epsilon with these indexes, with this random resampling, and recompute our Pearson correlation coefficient. Are people okay with this? Any confusion? So maybe the one strange thing is this IDX, which we saw last time, which is just a way of indexing into the vectors to pull out the variables, the elements that we care about. So play with it. It should become very transparent if you remove some of these semicolons and actually see what MATLAB spits out onto the screen if you're having some difficulty understanding what's going on. Okay, so now what we want to do is compute the confidence intervals, and so we're going to do that by making a histogram. And so we're going to make a histogram of all our Pearson values. We're going to have 100 bins. You could make that different. You could have coarser bins by sort of coarser chunks by reducing this value, or finer chunks by increasing it. And we're going to turn our probability, our counts, into a probability. So when you make the call to hist, you'll remember you'll get out the counts in each bin and the location of each bin. If we divide the counts by the sum of the counts, you get a probability. And if you do a cumulative sum of the probability, you get a cumulative probability. So we're going from counts to a probability distribution to a cumulative sum over that probability distribution. And so this is going to look something like, we're going to start with some bins and some counts. And so maybe this is like 1, 2, 3. So this is a histogram. We all like histograms. We all understand them. If we normalize by the sum of each of these bars, we're just going to turn it into a probability distribution. And so probability density function over the bins, where it's just a normalized distribution. So it's maybe 0.01, 0.02, 0.03. And then we can do a cumulative sum over the bins and compute the cumulative probability distribution. And so we just sum each of these things up. And so it's a running total. And so this is the cumulative distribution. It's just the sum of each bar as you move left to right. So people okay with this? Okay. So that's all that we're doing there. And now we actually just want to compute so let me go back. What we asked for, go back to the original Pearson test, was 95% confidence intervals. So we want to compute the 95% confidence range. And so we're saying alpha is 5%. That's why alpha is 5, because we want the 95%. You could change that if you care about some other number. And so then all we're doing is we're asking MATLAB to find where the cumulative probability is less than or equal to 0.05. And so we want to find the first time we hit 5% in our cumulative probability, because that's going to define the 5% low tail. And we want to find the first time that happens and the last time that happens. Because you can imagine as you're running through the cumulative probability distribution, maybe this is 1%, 3%, 7%. And so we want to find the last time this value is less than 5%. And so it's going to be this guy here. So this is, imagine this guy was 7%. So we don't want him, we want him. And so this defines the 5% tail. So it's a little weird because there's lots of arguments here. So you have a condition. You say how many conditions you want MATLAB to spit out, and you can say whether you want the first one or the last one. And so the last one is the one you want here. You want the last element of the cumulative probability distribution before you hit 5%. Okay, so if we then go and access the bin corresponding to this index, we will find the 95% low confidence interval on our distribution. Then we do the same thing for the high side. And so we want to find where the cumulative probability distribution is greater than or equal to 95%, and we want to find the one time that happens and the first time that happens, because that's going to define the 95% tail, the high tail of our distribution. We get the index of the bin, and we go in and find the value of the bin, which is the Pearson correlation coefficient corresponding to that bin. So that's now defined the 95% confidence interval for our data. Does that start to make sense to people? So what have we done? Let's recap. We've computed Pearson correlation coefficients under a bootstrap by randomly resampling. Then we've drawn a histogram over that distribution, and then we've just found the 5% tail and the 95% tail of that histogram. And so we find the low 5% of Pearson correlation coefficient, the high 95% of Pearson correlation coefficient, and we say that those are our 95% confidence intervals. So if this thing is really fat, we're going to have very large confidence intervals, which means we don't have much surety about our data. If this thing is really skinny, we're going to have very tight 95% confidence intervals, which means we're very sure about our data. So it gives you this measure of spread. Okay, and then I've just made a fancy fprintf, which is sort of a formatted print statement. And so /n/n gives you two blank lines, and then I've printed the results. And so the results, %.0f stands for floating point number with 0 decimal places of precision and an arbitrary number of digits. So we saw that when we made the awk call, I think. So the syntax is very similar here. Percent tells MATLAB you're going to make a call to a format, in this case floating point, and the precision of that format. Percent gives you a percent sign. And so it's sort of funny. If you write percent, MATLAB's going to freak out because it's going to expect a format field. So you have to type percent in order to make it print a percent sign. So a little bit annoying. You just have to remember it. So that's this percent sign right here. And then I actually want to print the confidence intervals. So the confidence interval, 95%, is -0.48 to 0.58. Okay, so here's where I made an error. And so we found the 5% tail and the 95% tail. So in total, we have actually 10%, because we have 5% low and 5% high. So the bulk of the distribution is actually a 90% confidence interval. So if I wanted the 95% confidence interval, what should the value of alpha be? 0.025, exactly. Okay, so that was my mistake there. So if I wanted 95%, I need to have 0.025 there. Okay, so that's the bootstrap. So essentially a super powerful technique, and I actually use it in my research all the time because I have finite data and I want to do error bars on it. And so I don't know what the underlying distribution is, and so I do a bootstrap test on it. So it's super easy and super powerful. Any questions about that? Okay, so let's forge ahead. So this one I'm sure you've heard of. Everyone's done linear regression at some point. So Excel does linear regression pretty well. We do linear regression all the time. We have a predictor variable and a controlled variable, and we'd like to find some relationship between them to put the best fit line through the data. Okay, so the purpose of multiple linear regression is to recover a predictor of a scalar-dependent variable, y, as a linear combination of independent variables, x. And so when you have more than one independent variable, x, you need to do multiple linear regression, because you don't want to just regress on one predictor, you want to regress on multiple predictors. And so imagine you want to predict the height of a person. Perhaps their weight is a good predictor to use, and also perhaps their gender is a good predictor to use, and perhaps their nationality is a good predictor to use. And so maybe you could use those three things as predictor variables to make a prediction for their height by doing a multiple linear regression. So pretty simple. So what does the theory look like? And so if we write things out in full, it's very easy. We take our data point yi, this is our measurement of somebody's height, and then we take the predictors. So yi1 is maybe their weight, xi1 is maybe their weight, xi2 is maybe their gender, xi3 is maybe their nationality, and each one of those things is going to have a coefficient in front of it, which is going to provide the best fit to the actual data. So the thing we're trying to find are these betas. Is that clear to everybody? So if you're just doing a straight line, that's just finding the slope and the intercept. When you're doing multiple linear regression, it's finding sort of this more multidimensional thing. Okay, and so you can write it in matrix vector form like this, which you may have seen from your elementary stats classes. And the whole idea is that this is our data, predictor data. This is the thing that we're trying to find. We're trying to find the best fit to minimize the error. And so the whole idea is trying to minimize this error, and that gives you the best possible values for the betas. So the math is sort of interesting. It's sort of long, actually, how you do least squares regression. But of course, MATLAB does it all for you, so you don't need to understand all the mechanics. So this is officially the ordinary least squares estimate, and MATLAB will do all this stuff for you. Okay, so one of the important things are, whenever you're applying a statistical test, are the assumptions. And so we assume that we have a linear model. And so if you have very curvy data, your y is a sine function of the axes. Linear regression is not going to do a good job. And so you need to be pretty sure that a linear model is going to be okay for your data. And so the best way to do that is, first of all, make a scatter plot and see if it looks like it's pretty much linear. We assume that the x's are independent. If you have highly correlated x's, this thing will break down. And so you can do that by testing Pearson correlation coefficient between the x's. And if things are too correlated, you maybe drop one of them. So that's a nice thing to do. Start preconditioning your data. Homoscedastic means that all the x's have the same variance, so the same variability. If that's not true, ordinary least squares regression will fail, and you'll have to do something a little fancier. It's not that difficult, but that is an assumption. And no multicollinearity, meaning that the x's are precisely dependent, and so you sort of get collapse between the x's. That screws up ordinary least squares as well. So these things are not completely satisfied. Maybe that's okay, and you can still do it. But if there's strong violations in any of these, ordinary least squares is not the right thing to do, and you'll need to look up a more powerful technique, some nonlinear technique, or some, they call it blue estimates when this is not true. Okay, but we're taking a simple case right now. So actually in practice, it's super easy. And so our y variable in this case is going to be our sigma. Our x matrix is going to be epsilons and 1s. And so why is that important? So we have our sigmas, which are our y variables, our epsilons. We can make a scatter plot. You did that last time. And we're trying to put the best straight line through this. And so we need to have, let me go back one slide. If we just had the epsilons, so this is our sigma, this is our epsilon, it would mean that we were fitting a straight line that went through the origin. Maybe that's not what we want to do. Maybe we want to have some intercept of the straight line. And so the way we encode that is to add this sort of augment our system with a column of 1s. And so if xi2 is all 1s, then all this beta 2 does is shifting the intercept. So I'm sure you've seen this trick before. It's just allowing the data to regress not only on the epsilons, but have a finite intercept. Okay, so that's what we're doing there. So if we didn't have this column of 1s in our X matrix, we would be forced to do something like this. If we do, pen's running out. If we do have the column of 1s, we can have a finite intercept, and that will give us a better fit. So that's the whole idea there. And so we'll bring a pen next time. And so our Y matrix are a bunch of sigmas, sigma 1, sigma 2, sigma 3, etc. Or Y vector, I should say. And our X matrix is epsilon 1, epsilon 2, epsilon 3, and then 1, 1, 1, etc. Okay, so is that clear to everybody? So if it's not clear why this should give an intercept, run through the math yourself for a simple example, and if it still doesn't make sense, come and ask me. Okay, and so that's going to be our X matrix, and then the whole idea is we're trying to compute this beta. And so we're going to get two betas come out. We're going to get the coefficient that goes in front of the epsilon and the coefficient that goes in front of the 1, which is basically the intercept of the line. And so let's call it regress Y, X. We're going to get five things coming out: B, B int, R, R int, and some statistics. The most important one is usually the first one, which is B, and so this is our beta matrix, our beta values. So this is the value that goes in front of the epsilon, and this is the intercept of our line. So the slope and the intercept of our straight line. So, linear regression, MATLAB did it in about 0.2 seconds very quickly without any of the pain you have to go through in Excel. So really nice. The second call gives you the 95% confidence intervals on these beta values. So exactly the same way as we got confidence intervals on our Pearson correlation coefficient, you can get confidence intervals on your beta values. So it says, how sure are you that this coefficient in front of the epsilon is actually 0.2259, or could it have been quite different? And it turns out we're not very confident. There's a large confidence interval on 0.2259. There's a slightly smaller confidence interval on the intercept. So the intercept looks pretty solid. Yeah, question? You can, and so if you call this with a third argument, so it takes 2 arguments by default and an optional third, you can specify your confidence interval. And so by default, it's 95%. If you did regress yx 0.01, it would give you the 99% confidence interval. Yes, good question. This is the array of epsilons, so the error that we make. And so it's our regression prediction minus our actual data value. And so these should all be pretty small. Maybe you don't really care about that. And the 95% confidence intervals on those errors. And so if you start screwing with these values within this range, how big or small could you make the errors? And so maybe you care about this, maybe you don't. Usually these things are not very important. Okay, and then we have a few things coming out here. And so the R squared value, which Excel loves. And so whenever you make a straight line in Excel, it always gives you the R squared. What is the R squared? People don't always appreciate what it is. It's 1 minus the sum of squared errors over the total sum of squares. And so it's basically how much better of a job did you do by fitting a straight line as opposed to just representing the data by its mean. So I could take this data set, these sigmas, and just give you the value of its mean. And so if there was absolutely no variance in sigma, if they just lived along a straight line, the mean would actually be really good because all the sigmas are the same. If they lie off a horizontal line, so something like this, the mean is going to be a terrible estimate because there's large variance. And so what this R squared value actually tells you is how much better did you do by going through the pain of a linear regression as opposed to just representing the data by its mean. Okay, and so the higher this value, the better. And so it turns out in this case it wasn't that great. Okay, and then there's the F statistic and the P value. And so it turns out that the underlying statistic, the underlying distribution we need to worry about for doing multiple linear regression is not student P distribution, but actually the F distribution. And we can assign a P value to the regression coefficient. And so if this is low, it means we have high confidence in this, and we expect the confidence intervals to be narrow. If this is high, these values could have arisen just by chance. And so in that case, we don't have much faith in them. And so in this case, what is the probability that a finite value, so if this is 0, it means the data has no dependence on one another, it's just lying flat. If that is our null hypothesis, what's the probability this finite value of the slope could have arisen just by chance? It turns out it's 28.6%. And so we don't have much faith in the fact that there is actually a linear relationship in this data. Okay, so let me say that with some math behind it. So the F test assesses whether the fitted regression model gives a statistically significant better fit to the data than simply describing the data by its mean. That's what I just said in words. And so model 1, we just describe the data by its mean. Model 2, we actually go through the pain of a linear regression. And so what the F test is saying is how much better is this than this? And so the p-value is the probability of observing the particular F value that MATLAB spits out. Under the null hypothesis, the data is just described by its mean. And so again, if that is less than 5%, we say, okay, our linear regression model is good. If it's greater than 5%, it could have just happened by chance. And we say we don't have much confidence in our linear regression model. So are people getting comfortable with p-values, test statistics? You'll get comfortable when you do the project, but let me just try and introduce them to you. So come and complain to me when they don't make any sense. Okay, multiple linear regression. People okay with this? Okay, so let's keep going. So let's first take a little detour and say, when do you do regression and when do you do correlation? So when do you do a multiple linear regression and when do you do a Pearson correlation coefficient? And so it's very easy. And so you calculate linear correlation if you measured both x and y. And you want to say how well are they associated, at least in a linear sense. However, you choose linear regression if you manipulated x. And so if you have control over x, you want to do a linear regression. If you don't have control over x, you want to do a Pearson correlation coefficient. So when you're measuring people's weights and heights, you don't have control over people's weights and heights, so correlation coefficient is the right thing to do. When you're in the lab, figuring out how the current depends on resistance, you're maybe manipulating the current, manipulating the resistance by determining what size of resistor you're putting in your system. And so then the resistance is a manipulated variable, and you want to do linear correlation. You want to do multiple linear regression. So the other important thing is that linear regression calculations are not symmetric with respect to x and y, and so you'll get a different answer if you do regress x on y or regress y on x, and usually one makes sense to do and one does not. Whereas Pearson correlation coefficients are symmetric with respect to x and y. It doesn't matter what order you put them in. And that sort of makes sense because in the Pearson correlation coefficient, you're saying how well associated are these two things. Whereas in linear regression, you're trying to build a predictive model based on one variable to predict another. And so clearly that is going to then depend on the order. Okay. Akaike information criterion. Has anyone heard of this? So this is getting a little fancier. So I'd be very surprised if anyone has heard of this. This is actually really cool too, and it's actually really easy. So the purpose of this analysis, the Akaike information criterion, AIC. There's also one called the Bayesian information criterion, BIC. AIC is better for various reasons. This is asking what model should I choose? And so imagine you have some data, and you want to know whether you should just describe it by its mean, whether you should describe it by a straight line, by a sine curve, by some crazy exponential function, by some crazy polynomial of order 42. What is the best one to choose? Clearly, as your model gets more and more complicated, you're going to do a better job of fitting the data, but at the expense of having a more complicated and difficult to interpret model. So what is the best trade-off between fitting the data and model complexity? The AIC answers this for you in a very quantitative and simple way. So let me motivate this by a quote from John von Neumann. With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And so Jim Wei, who's now chemical engineering professor emeritus at Princeton, he was dean of engineering at MIT, took John von Neumann seriously and actually wrote a paper with this. And so let me see if I can read what's written here. How many parameters does it take to fit an elephant was analyzed by Wei. He started with an idealized drawing A, defined by 36 points, and used a Fourier sine series to fit it. He estimated them for K5 equals 10, K equals 5, 10, 20, and 30, and stopped with a 30-term model. So this is the fun part. He concluded that the 30-term model may not satisfy a third-grade art teacher, but would carry most chemical engineers into preliminary design. And so you can decide whether or not that's true. I'm inclined to agree with him. Okay, so it's a little bit of fun, but basically the idea is you can make things more and more complicated and get a better and better fit, but are you statistically justified in doing that? And so the AIC gives you that answer. This may not have been something you've thought about before. So maybe when you're making plots in Excel or MATLAB, you just pick the polynomial order that sort of looks best. But what grounds do you have for saying that that is the best one? This will answer this. So it's an information theoretical measure. It basically is an estimate of the information lost relative to some true model. So we don't know what the true model is. We have to sort of estimate it, or at least do things self-consistently. And so it does exactly what you would expect. It penalizes more model parameters and penalizes poor fits. So if you have a model with lots of parameters and a poor fit, it's going to get very heavily penalized. If you have a model with very few parameters and a good fit, you're going to get, a good boost from the AIC. And so this is what it looks like. The AIC is 2K, where K is number of model parameters, minus 2 log L, where L is the likelihood of the model given the data. And so don't be scared of this thing. It's just a sort of subtraction of 2 terms. And it turns out for most things that we ever deal with, if you assume your data is identically and independently distributed, this likelihood can be expressed in a much more simple way, which is basically the RSS, the residual sum of squares. And so we remember the residual sum of squares. You fit your linear model, you have your data. The residual sum of squares is the sum of the squared deviances of the data actual values from your predicted model along this line. So if you let me go back just a couple slides for a second. When we got MATLAB to dump out all of these errors, if we squared all of these and summed them together, we would get the residual sum of squares. And so that's an easy way to get the RSS. Okay, and so the AIC simplifies to this form when we make the assumption of independently identically distributed data, which is usually a pretty good assumption for most things that we will do. And so then you can just compute this yourself in one line. So you can figure out how many parameters your model has, K, times it by 2, add on N, the number of data points that you have. So in this case, we were looking at, we said sort of 5, but of course we'll usually have more than that. Logarithm of the RSS divided by 5. And that gives you the AIC test statistic. So you can compute this for various models and then figure out which is the best. And so the best is the one with the lowest AIC value, because you don't want to get penalized by bad fits or penalized by large numbers of model parameters. So you could do this for any sort of model you care. You could do some nonlinear fits, you could do various degrees of linear fits, you can do polynomial fits, Fourier fits, whatever you care to do, and compute and assign an AIC to each one. Does that sort of make sense? It's sort of a very intuitive idea. I don't know why we don't use this more, but it's really cool because it tells you which model you should pick. So let's do a simple example. You're going to do this basically in your homework. So let's use the AIC to discriminate between 3 different regression models. So our first model is the simplest one we just talked about, which is regressing a straight line, basically. And so sigma equals beta 1 epsilon plus c. What about if we had either quadratic terms? Does that make things much, much better? And do we have statistic justification to do that? So beta 2 epsilon squared plus beta 1 epsilon plus c. Or what about if we had the power 3 term? And so the fits are going to get better and better because the models are getting more and more complex. But are we justified in going to more complex models? Does the data justify a more complex model? The AIC tells you this. Okay, so how do we do this in practice? This is a little bit, looks a little bit intimidating, but really it's very easy. And so our y variable is sigma. Capital X1 is epsilon and 1. And so that's a matrix where the first column is the epsilons, the second column are 1s, exactly what we did before. X2, we just have a bigger matrix with epsilon squared, epsilon 1s, and then X3 obviously is epsilon cubed, epsilon squared, epsilon, and then 1s. And so just adding more and more terms to our model. Then we just make our regression call on yx1, yx2, yx3, get all the stuff out of it and store it in these variables, which is exactly the same call we made before. We've just suffixed everything with a number to keep track of which model it pertains to. And then we're actually going to do the AIC stuff. So is everyone okay up to here? So it's basically just 3 different regression calls, exactly the same as we did before. Okay, so let's do the AIC. So n is the length of sigma, so that's the number of variables that we have. So that's the n value. K is the number of model parameters, and so that's 2 model parameters, 3 model parameters, and 4 model parameters. The RSS is going to be, we dumped out the epsilon values for every data point, and so if we square those and sum them together, we're going to get the RSS, the residual sum of squares. A clean way of doing that is a vector product. So you take the R1 is going to be a column vector. If you transpose it and get the row vector and multiply the row vector by the column vector, you do that operation. You square every element and sum them together. It's just a quick way of doing that. So it's just taking a row vector into a column vector. So this is 1 by n. This is n by 1. So you're going to get a 1 by 1 scalar out the back end. So it's going to be the sum of the squares of the epsilon. So you can do it any way you care to. This is just a clean way of doing it. Okay, then we're just going to do for I equals 1 to 3, and we're going to compute the Akaike information criterion for each one of our models, 2 times k, the particular value of k for the model, n log RSS for that model divided by n. And then we're going to print the AICs. And so the AICs look like this. And so it's negative 83, negative 82, and negative 85. And so in this case, the lowest AIC is negative 85, and so it tells us from these 3 models, we are actually justified in picking the third one, because it has the lowest Akaike information criterion. We get a much better fit at the expense of a few extra parameters, and the trade-off is actually in our favor. And so the AIC goes down. So from these 3, what can we say? The third one is the one we should pick. Of course, this is always a finite sample, so it doesn't say that this is the single best model in the world, because we haven't tested all the models in the world. But of these 3, if we had to pick one, we would pick the third one. So there's one final important point. Beware, the AIC measures only relative and not absolute model quality. So if you compute the R squared value for these 3 models, they're all horrible. And so the R squared value for model 1 is like 0.05. Model 2 gets a bit better, 0.1. Model 3, 0.3. But they're still all horrible. And so we say that these models are all horrible. If we had to pick one, we'd pick the third one. So that's sort of a subtle point. You need to worry about things in an absolute sense and also relative sense. This is really cool. So this is a way to justify your model selection, which is sort of very valuable in whatever sort of data analysis you're doing. So people okay with this? Okay, so let's do cross-validation. So has anyone heard of cross-validation before? Okay, so the purpose of cross-validation is sort of taking our model and trying to test it on new data. So Imagine we were able to build a regression model of weights versus heights of all the people in this room, and we thought we had a really good model. How could we test that? We could go to the classroom next door and make a prediction using our model and see how well it lined up against the actual heights of the people in the classroom next door. That'd be a fine thing to do. What about if you don't have access to more data? One thing you could do is maybe make a model on this side of the class and then test it on this side of the class. But maybe that's a bad thing to do because your model has only been trained on sort of half of your data. So you're throwing away half of your data and just using it for testing rather than actually model building. So cross-validation is the way of using all of the data to build the model and then sort of in an internally consistent way testing the model on the data that's accessible to you. So let me jump to the punchline. Basically, one of the best ways to do this is leave one out cross-validation. So you would build a model of height versus weights for everybody in this room except one person, and then you would test the model predictions against that one person. You would then pick a different person to leave out, pick a different person to leave out, until you'd built a model on everybody except one person for every one person in this room. So why do we do that? Well, because we build a model on data and then test it on new data. You don't want to be testing your model on the same data you trained it upon. That's sort of like cheating. And so by doing leave one out cross-validation, it's a very efficient way of using the bulk of your data to build a model and then test it on just one data point. And then, of course, by testing on all single data points you leave out, you can get an average of the model performance. So we'll go over this again. So that's basically the idea. You can think of it as an alternative to AIC for model discrimination because you would want your models to do better and better without overfitting, and so that's the important part here. You can make your models more and more complex, and so they do a really, really good job of reproducing the data you train them on, but then when you try and test them on a new data set, if they're too complex, they're going to start to fail because they're just overly complicated. There's too many parameters. They do a great job of the data they were trained on, but they're not extensible to new data. So we want to have a trade-off of a good fit and sort of good extensibility, so no overfitting. Okay, and so the mean squared error, so the residual sum of squares, basically measures, it's an optimistic prediction of how good your model is because you're only testing it on the data your model was trained upon. If we break the data into training and validation sets, in addition to the mean squared error, the residual sum of squares of your model, you can get a cross-validation analog of it, which is basically the mean squared error of your model on new data. So does it overfit or does it underfit? And so the two ways to do it, like I said, leave one out cross-validation is sort of my favorite way of doing it. You can also do k-fold cross-validation, where you split the room into, say, 10 chunks. You build a model on 9 of the 10 chunks, test it on the 10th chunk. And that would be one round of cross-validation. You would then pick a new chunk to leave out, build it on the other 9, test it on the chunk that you left out, until you've done all 10 chunks being left out. So it's sort of very similar to leave one out. It's just on the basis of chunks rather than single data points. So this sort of makes sense. People are sort of comfortable with this idea. Training a model on some of your data, testing it on the other chunk of your data. That's basically the way to think about it. And we'll see why that's important in practice in just one second. So I think you're going to do some cross-validation in your homework also. So you hack this code to sort of do that. But let's do this together on the board. Let's use leave one out cross-validation to discriminate between 3 regression models. So these were the 3 we looked at with the AIC. Let's do some cross-validation to try and discriminate between them. Okay, so let's first of all start with some standard ordinary least squares regression. And so what we're going to take here, we're going to look at the first model, so model I. This all pertains to model I. We're going to take our X matrix, which is exactly as before, column of epsilons, column of ones. We're going to take our Y matrix, which are sigmas, and we've got n data points. We're going to do a regression, and we're going to compute the mean squared error. And so the mean squared error is just the mean of the RSS. And so you can compute the residual sum of squares and take the mean. So it's the mean of the sum of the squares of the residual errors. Okay, so that's a standard linear regression. We've done that twice now. So how do we do the cross-validation? So we're doing leave one out cross-validation. We're going to build an array for our cross-validation mean squared error. And because we're doing leave one out, we're actually going to do n different rounds of cross-validation, because in each round we're going to leave out a different data point. So we're going to pre-assign our array to have n elements in it. Okay, so let's do our n rounds of cross-validation. So p goes from 1 to n. So let's build the leave one out independent variables. And so idx is set diff 1 to n of p. What the heck does this mean? It's the difference between 2 sets. This is a call that makes a difference between two sets. So our first set, if we imagine that n equals 5, is 1 to n, which in MATLAB parlance looks like this row vector. And then we're taking the difference of that row vector with p. And so in this case, the first time we hit the loop, p is equal to 1. And so if we take the difference, the set diff between these two things, we're going to wind up with 2, 3, 4, 5. So this row vector, where it's the difference between these sets. We're going to take this element out of the first set. So it's a clean way of getting a nice indexing where you leave out one of the indices. So imagine we've entered this loop on sort of our third round, and so p is equal to 3. If we do set diff 1 to n and 3, what is this array going to look like? It's going to be 1, 2, 4, 5. So in this case, we've left out the third element. So pretty quick and simple way of making these indexing. Okay, so we're going to then use IDX to index into our epsilon and our sigma arrays to leave one out from the training data. And so when we're building our X matrix, now it's not all the epsilons, but just the epsilons that we're going to index with IDX. And instead of being a length n column vector of 1s, it's going to be a length IDX column vector of 1s. So we've omitted the p data point from our linear regression. Okay, so then we're going to do our linear regression. We're going to regress y with indexing IDX and x and compute our standard regression statistics. And then we're going to actually do the cross-validation. Okay, so up to here, what have we done? We've trained a linear regression model on all of our data except one data point. Now we're going to test how well our linear regression performs on the data point we left out. How do we do that? We take the single x value that we left out, so it's going to be the epsilon of the piece epsilon value, and of course we need to worry about the second column, which is the 1. And then we're actually going to run our regression model on that data. So this is where we're running our regression model. We got our beta parameters. If we multiply them by x solo, we're actually going to get our prediction for y. And how well did that line up with the actual value of y? So the piece value of y in our data array minus our prediction for the piece value of y. So that's what's happening right here. We're going to square it, and we're going to dump it into this array that we've pre-assigned. And so this is the mean squared error. Sort of mean is a misnomer here because there's only one data point. But it's a squared error off the model that we trained on all the data except that one data point. People was comfortable with that? We've trained a model on n minus 1 of our data points, and we've tested it on the remaining data points. Okay, so then we square the error, store it in this array, and then we cycle around this n times, each time leaving out a different data point to do the test upon. Okay, so we get to the end, and then we just take the mean of this array in which we've been storing our square errors, and that's our cross-validation mean squared error, as opposed to the standard mean squared error of our model, which is sort of an internal test. This is now an external test of our model. And so then we can just print some nice stuff out as we did it in the original regression call. So what happens if you run this for various models? So this is the mean squared error for model 1. And so this is what we did before. You just run your regression model, you compute the mean squared error, and this is the value. You get 0.0154. The leave one out cross-validation mean squared error is 0.0213, which is doing all this stuff. You can do exactly this, but for model 2 and for model 3, and you can get these values, and then you can plot them. And so what is this telling us? So this is sort of a horrible data set to do any analyses on, and so because nothing interesting usually happens. And so what are we actually seeing here? You're going to see much more interesting stuff in your homework, by the way. And so if you look at the mean squared error, we see that as we increase model complexity, so the highest power in the model, the mean squared error gets better. So that's a good thing, because we're doing a better job of fitting the data. But what immediately happens is that you start to overfit any new data that you pull into the model, so, which we tested by doing cross-validation. So the mean squared error goes up in a cross-validation sense as your model gets more and more complicated. And so we begin to overfit. And so maybe what this is telling us is that we need to trade off doing a good job of fitting the training data with a good job of fitting external data. And so how might you make this trade-off? Well, it's really up to you. Ideally, what we like to look for is sort of a minimum in this curve right here. So if you see a minimum in this curve, that tells you sort of the ideal model to pick, because you're sufficiently complicated, you're doing a good job of fitting an MSE, but you're not overfitting your external data. So if this has a nice minimum in it, then you're doing good. If it doesn't, your data doesn't sort of tell you very easily which model quality, which model power you should pick. Okay, so that's cross-validation. People okay with this? You'll get some practice with this, but if you have the idea in your head, then that's enough, and you can start using the code for your own purposes. Okay, so last one, student t-test. So has anyone heard of this? So we talked about the student t distribution at the beginning of class. This is the student t-test. So I think this has an interesting provenance. And so student, I think, was a mathematician who worked for the Guinness Brewing Company in Ireland. And he was on the payroll, and he was doing quality control for all the beer that they were brewing. And he was a mathematician. And so he wanted to publish all this cool stuff he was using to produce better and better beer, but his employer wouldn't let him, and so he had a pseudonym, which was student. So I believe that's where this came from. Okay, and so it's got an alcoholic provenance, so we're going to use it for good rather than for evil. So okay, so the question this answers is, are two data sets significantly different? So let's stick with our height example. If we make a histogram of the heights of the folks on this side of the room, a histogram of the heights of the folks on this side of the room, are those distributions very different? So you could think, well, maybe they are very different, they look very different, but can we assign sort of a statistical value to how different they are? Or are they fundamentally just different manifestations of the same underlying distribution? So that's what we're trying to answer. Okay, so the theory assumes the data sets are independent, the data sets are normally distributed, and that they're small sample sizes. If you violate any of these things, you have to use something different, related tests, but slightly different. So for large sample sizes, you might use something called the z-test. You can look that up if you're interested in looking at large sample sizes. For non-normally distributed data, you use something called the Mann-Whitney test. But we're going to focus on small data sizes, normally distributed. Student t-test is the right one to use. So how does it work in practice? So you have two data sets. So imagine we had height 1, which are the heights of the, height 1 of group 1, which are the heights of the students on side 1 of the room, and this is the count. And so you could develop some histogram that looks like this. H-E-I-G-H-T. So this is group 1. And then you could also generate a histogram of the heights of the people on the other side of the room, on part 2. So if I had different colored pens, I would draw this differently. I'm going to do it with dashes instead. So imagine their histogram looks something like this. And so the question you could ask is are these two distributions different? So are they drawn from different, or is this data drawn from two different distributions, or is this data drawn from the same distribution? There's different manifestations of the same distribution. So you might say, well, they look pretty different. The bars are different heights, and this one has a longer tail, but that's not really satisfactory. So can we make a sort of numerical assignment to how different they are? So the way you do this is the following. So you will never need to do this. So this is what's happening under the hood of MATLAB. You basically make a one-line call, and it does all this stuff for you. But it computes this test statistic, which is known as the t-test, and it computes the number of degrees of freedom using this, and then it appeals to some underlying files that it's got built into its file system that have those particular student t distributions, and it compares your data to that. Okay, and so basically these are the means of your data set, these are the variances of your data set, these are the number of samples in each data set. So don't worry too much about this stuff, but this is what's happening. It gives you a test statistic, gives you degrees of freedom, then MATLAB knows to go in and pull out the correct student t distribution against which to compare your data. Okay, so student t distribution looks a lot like the standard normal, just a little bit weirder. So it looks like a Gaussian, just a little bit weirder. So don't worry too much about this stuff. Okay, so last slide. So how do we actually do this in practice? So through an example, let's ask the question, do the sigma parameters for TIP4P water models differ significantly from the sigma parameters from the rest of the water models? So if you open up your file water_models.csv, you will see that some of the models are called TIP4P something, and some of them are called different things. So what we're going to do is we're going to pull out all the sigmas belonging to tip 4P guys, pull out all the sigmas belonging to everybody else, and ask, do those sigmas belong to the same distribution or a different distribution? So if they belong to a different distribution, that might tell you something about tip 4P, that it's doing something different with sigma than the rest of the models are. So maybe that's interesting. It's almost certainly not interesting, but let me just illustrate the point. Okay, so we're going to split up the data. So we're going to take our sigma vector, and it turns out the elements 8 through 13 pertain to the tip 4P water models. So we're going to pull out sigma 8 through 13 into sigma tip 4P, and then we're going to have this other vector, sigma rest, which is basically the rest of the data. And so a clean way of doing that is to set diff between 1 to the length of sigma and 8 through 13. So this will give you 1, 2, 3, 4, 5, 6, 7, 14, 15, 16, 17, 18, all the way to the end. So you can do this however you care to, but this is a quick way of doing it. And we're going to ask for a sort of precision, or precision isn't the right word. We're going to ask for an alpha, a significance level alpha of 5%. And so, like we said before, you could make this 1% or 0.1% or 10%, whatever you would like. But we're saying the cutoff is going to be 5%. If our p-value is less than 5%, we're going to accept that they're different. If it's greater than 5%, we're going to say we don't have faith that they're different. So let's see that in practice. So how do we perform the t-test? So very easily, just in one line. And so the call is t-test 2. So why is it t-test 2? Because we're having two independent samples. Then we need some parameters. And so we've got some arguments. And so we've got our tip 4P sigmas. We've got the rest of the sigmas. We've got our alpha, which is our significance level of 5%. Then we've got two arguments, both and unequal. So both just means that the means of the two different data sets are not equal. That's more general than telling MATLAB the means have got to be equal. So you always use both. You always use unequal. Both and the variances are unequal is the second part. This says whether the means are equal, whether the variances are equal. And so typically we want to be as general as possible and not constrain those things to be equal. Okay, then it's going to run the test. And so what test are we doing? The null hypothesis in this case is that the data are drawn from the same distribution. So this is the null hypothesis we're going in with. So let's skip this first one for a second and look at the second one. So P is 0.2043. And so what does this mean? The value of the test statistic that MATLAB computed, this T value that we saw in the last slide, the probability that we would see that value just by chance if the null hypothesis was satisfied, if the data really were drawn from the same distribution, is 20.43%. That's a high probability. So that means that there's a 20% chance that this value of the test statistic could have arisen just randomly. And so our significance level is 5%. And so because 20% is bigger than 5%, we cannot reject the null hypothesis. We cannot reject the idea that the data could just be drawn from the same distribution. And so that's why this H comes out as 0. So H stands for hypothesis. And so H equals 0 means that we have to accept, or more precisely, we cannot reject the null hypothesis. If H comes out as 1, it means we can reject the null hypothesis. And you can double check this because you see that this p-value is greater than the significance that you specified. So are people okay with that? We're coming in with some null hypothesis and we're asking MATLAB to test whether that null hypothesis is true or not. Null hypothesis is data are drawn from the same distribution. Okay, and then we have confidence intervals at that particular alpha. In the t-test statistics, that's usually not that important. And if you're interested in computing the critical t-value, so the t-value above which you have to hit at a significance level of 5% for the hypothesis to be rejected, you can compute that. That's usually not that interesting either, because basically all that information is contained in here. So this is good. So you're actually going to do in your homework, I'm going to give you some data on some steels of two different classes, and you're going to determine for your project, whether that data comes from the same underlying distribution, whether the steels manufactured in different plants, for example, have the same distribution of strength, or whether the distribution is basically the same. So for quality control, for brewing beer, or for doing anything else, this is a really nice test to be able to do. Okay, so that's it for today. So it ran a little longer than I expected, but I will stick around for the next 10 minutes if folks want to ask any questions about homeworks or anything in the lecture notes. And otherwise, we'll see you next Tuesday. All right, have a good weekend. Thanks, folks.